So hi, everyone. Welcome to the afternoon session of our last day of our workshop. So I have the pleasure to introduce Harmony Zhan. She did her PhD with Chris Gatzel, where she wrote a very nice PhD thesis on the topic of discrete time quantum walks. So I'm really looking forward to hearing her tell us more about it. Please take it away, Harmony.
Thank you, Crystal. So before I start, I want to thank all the speakers for their wonderful talks and the participants for attending this workshop. So I hope you enjoy this as much as I do. Okay, so let me get started. Here's my plan. First, I will introduce a somewhat different type of quantum walks called discrete quantum walks. And then I will show you some examples of state transfer, including perfect, pretty good, and close enough state transfer. And after that, I will discuss the relation between all these phenomena to Hermitian adjacency matrices of various graphs. And finally, I will discuss briefly on the relation to quantum walk search. Okay, so what is a discrete time quantum walk? Here's a graph on 4 vertices. It's called the diamond graph. And here's the transition matrix that governs the whole evolution of a quantum walk. So if you are familiar with continuous time quantum walk, you may see a lot of differences here. First of all, this is no longer a 4x4 matrix indexed by the vertices of the graph. Okay, instead, it's a huge graph, and the indices are actually all the edges in both directions. So because the diamond graph has 5 edges, we get a 10 by 10 matrix. Okay, that's observation number 1. And number 2 is, although this matrix is large, it's quite sparse. And the non-zero entries can only appear at very specific locations. So for example, let me highlight one column. This guy indexed by the arc pointing from 1 to 0. So what are the non-zero entries appearing here? Well, there is -1/3 corresponding to 0, 1, and there is 2/3 corresponding to 2, 1. And finally, there is 2/3 corresponding to 3, 1. Okay, and all these arcs I highlight here are entering the vertex, the same vertex 1. Okay, and on the other hand, the column index is an arc going out of 1. Okay, so that's called a locality condition for discrete quantum walk. So after every step, you can only move to an adjacent arc. You cannot jump too far. And finally, among all these arcs here, there's one special arc that's the opposite of the original arc. So 0, 1 and 1, 0, they are a pair of opposite arcs. And that's why the value it gets in the entry is different from the others. And I will talk more about this in the next slide. Okay, so in general, given the graph undirected, the state space will consist of all unit vectors indexed by the arcs of the graph, or you can view it as a function that assigns every arc a complex number, normalized, of course. And then the evolution is determined by a unitary matrix indexed by the arcs, which sends every arc, okay, to a linear combination of the arcs entering the tail of the original arc. And the coefficients are also very easy to describe. If the arc is opposite to the original 1, then you take 2 over the degree of the tail minus 1. Okay, and all the other arcs gets equal amplitude, which is 2 over degree of u. Okay, so knowing the graph is enough to know the transition matrix in this specific example. Okay. So an interesting thing about quantum walk, like discrete case quantum walk, is that for the same graph, you can associate it with different transition matrices. And to see that, sometimes it's easier to see that by describing U as a product of 2 matrices, both of which are decomposable. So here I'm writing U as R times C, where R is called arc reversal matrix and C is called uncoiling matrix. So I will talk about C first. If you order the arcs according to the tail, so here all the arcs are leaving 0, and here all the arcs are leaving 1, and so on, then in this ordering, the coin matrix is block diagonal. Okay, And all these little blocks are unitary matrices. They are called coins that you assign to every vertex. And physically, this means something similar to flipping coin in a classical random walk, where you decide whether you want to move left or move right. Here, the original direction is pointing from 1 to 0. And then after you flip a coin, you may change your direction to, well, you may stay in the original direction or change the direction to the other arcs leaving 1. Okay, so that's step 1. After you flip the coin, you need another matrix that changes your tail so you don't get stuck at one vertex forever. And that matrix is called the arc reversal. So it's very simple. It simply swaps the tail with the arc, the tail with the head of the arc. So in another ordering of these indices, you can represent R as also a block diagonal matrix where each block is 2 by 2 of this form, 0, 1, 1, 0. Okay. So technically speaking, there's no restriction on the coins other than being unitary. But for this talk, I'm gonna consider only the coins that have order 2 and they are Hermitian. So in the previous example, the blocks all look something like this. It's 2 over the degree of the tail times O1's matrix minus the identity. And this is called the Grover coin. It first appears, I guess, in the Grover search algorithm where you assign these to almost all the vertices. And later, Camden generalized this model so that you can run a quantum walk on any graph with a Grover coin assigned to the vertices. Okay, now if you think about this, J is really a projection onto a space spanned by the O1's vector. Okay, now you don't have to assign 1 in this vector. Instead, you can put arbitrary weights, and with that slight change, you obtain this weighted Grover coin. So, for example, suppose your vertex has degree 2, then this guy, if W equals root 2 plus 1, then I believe with that W, you will get the Hadamard coin. And that has also been studied a lot on the infinite paths and the cycles. And when your vertex has larger degree, the general case is also studied in a paper by Higachi and others in 2014. And I think they call this a twisted Zaglis walk. Okay, and finally, you can also consider the opposite of the Grover coin. And this is extremely useful if you want to find a marked vertex in a graph. So here what happens is you assign the usual Grover coin to many vertices, but there will be some special vertices that you give them this negative version. And then your goal is to start with the constant vector and land on those marked vertices after a few steps. And that's discussed in many papers. Okay, so yeah, so that's what I want to talk about, the coin. Now, suppose you have a target state in mind, and then you also have initial state X. After you run the quantum walk T steps, how close is your current state to your target state? So in a continuous time quantum walk, when we talk about moving between vertices, we mean sending the characteristic vector of a vertex E sub A to that of another vertex E sub B. But in a discrete quantum walk, this is slightly different. When we say moving between vertices, we actually mean moving between the outgoing arc of a vertex to the outgoing arc of another vertex. So a typical initial state would be something like, say, a uniform superposition of the outgoing arcs of the left vertex. Okay, and the target state may be also a uniform superposition of these arcs for another vertex. And we say there is perfect state transfer if there exists a T. Usually this is assumed to be an integer, so that the state at step T is exactly Y up to some unobservable scalar. Okay. And correspondingly, when we talk about probability at a vertex, we mean the sum of the probabilities over the outgoing arcs of that vertex. So you can visualize those in these animations. Okay. So this is just one example that shows that PSC occurs at step 6 from left to right on this cocktail party graph. Okay. And we cannot always aim for exact state transfer, but something similar may occur. So for the hypercube, again, I'm going to start with the uniform superposition of these arcs. And then if you focus on this vertex and stare at it for long enough, then you will see the probability gets above 0.3, 0.5, 0.7, 0.9, and even higher. So in fact, for however small epsilon, okay, and for this particular example, you can always find an integer time t so that your state is epsilon close to your target state. And that's what we call pretty good state transfer. Okay, finally, sometimes we don't even aim for this arbitrary precision. All we want is to go above a threshold. So suppose for a small enough epsilon, if I can get close to the target state within this precision, then we say there is close enough state transfer with respect to epsilon. And you will see this type of state transfer quite often in a quantum search algorithm. So here, the evolution is slightly different. I assign the Grover coin to all these vertices. Okay, so this will be Grover coin. And the specific vertex on the left-hand side will get minus Grover coin. And then we're gonna initialize our state in equal superposition of all the arcs. So let me see if I can stop at time 0. Okay, so this is the probability you observe initially. And then as t increases, you will see that the probability starts to differ between these vertices. In particular, the left one gets something around 0.3, while all the others are relatively smaller. So in a sense, if you do a measurement, you have a higher probability of finding this vertex. And well, depending on your epsilon, this may be good or not good. Okay, so all the phenomena I talked about in the previous slides can be studied using spectral information of the transition matrix. And for example, let's look at the pretty good state transfer. Some of you may be familiar with this characterization here. It's very similar to the continuous case. So basically, suppose this is the eigenvalue of your transition matrix, and FR is the eigenprojection onto that space. And we call an eigenvalue, we define the eigenvalue support for your initial state to be the set of eigenvalues for which that projection of X onto the R's eigenspace is non-zero. Okay, and then PGST occurs from state X to state Y if and only if the following two conditions hold for the eigenspace and the eigenvalues. So the first one says X, Y as states, they are strongly cospectral with respect to the transition matrix. That is, this projection is a scalar multiple of that projection. And we want this scalar to have unit norm. And this condition must hold for every eigenvalue lying in the eigenvalue support of X. Okay, and given that X and Y are strongly cospectral, the second condition says that to approximate Y, it's enough to approximate these scalars using some integer t and a fixed gamma. So to be more precise, there exists a gamma with unit modulus so that for however small epsilon, you can find the time t such that for every eigenvalue in the eigenvalue support, these two numbers are close enough. Okay, so if you have a continuous quantum walk, then all of this can be stated in terms of the spectrum of the underlying graph. So theta r will be a graph eigenvalue, fr will be a graph eigenprojection, and if x and y are real, which is usually the case, then we know alpha r has to be plus minus 1. So we can further divide this into the plus set and minus set. And then you can apply Kronecker theorem to reduce this further into some number theoretic conditions. However, in the discrete case, it's not clear. like how U is related to the underlying graph. So the next question we are going to talk about is, what do the spectrum of U have to do with the graph if you change the coins? Okay. So in general, the relation is not clear, but because we already assume our coin is order 2 and Hermitian, this is somewhat manageable. So in the case when R squared and C squared is equal to the identity, you can decompose your state space into a direct sum of invariant subspaces under R and C. And moreover, each of the subspace has dimension at most 2. So now to diagonalize U, you just need to diagonalize it inside each of these WIs, and that's equivalent to solving a 2x2 linear system. And all these one-dimensional invariant subspaces will give you real eigenvalues of U, which have to be 1 and -1. And the two-dimensional subspaces give you a pair of conjugate eigenvalues that are determined by this matrix. So yeah, I haven't told you what N is. Because C is a reflection, you can write it as twice a projection minus the identity. And then you can just take an orthonormal basis of the space you are projecting onto and put them as the columns of N. And this will give you precisely the projection. Okay. So once you have that matrix, which is usually smaller than U, then you can consider this Hermitian matrix. And by interlacing, its eigenvalues lie between -1 and 1. And those eigenvalues are exactly the real part of the eigenvalues of your transition matrix. Okay. And the eigenvectors of this Hermitian matrix can also lift to eigenvectors of U by this matrix and your arc reversal matrix. Okay. I see. I just saw the chart. Sorry. Where do the numbers come from? Yes, it's coming from the global coin. So yeah, you don't have to assign the same numbers to all the outgoing arcs except for the first one. There are many ways to put the weights and related to a meaningful Hermitian adjacency matrix of the graph. And I guess I was wrong about where the global coin come from. Tom has corrected me in the chat. Okay, now, yeah, I haven't told you what's the relation between U and the underlying graph. So everything boils down to this Hermitian matrix, and we should take a closer look at what this is equal to. Now, consider the usual global coin, which is just this plain old-fashioned 2 over kj minus I. You can expand this as the following. So 1 over root k times all ones, okay, and times its own transpose. Now this guy is indexed by all the outgoing arcs of your vertex. So you can view it as a function that assigns the weight 1 over root k to every outgoing arc. So for example, if your global coin is assigned to 0, then here you have 1 over root 2, 1 over root 2, all these two arcs. Now, once you stack all these global coins together, what you get is a matrix that records all these assignments in every row. So besides the one we just talked about, you see these weights for vertex 1 and these weights for vertex 2 because they both have degree 3, and the same weights for vertex 3 as those for vertex 0. Okay, and now it's an exercise to show that this product is really just a normalized adjacency matrix of your graph, and here D represents the degree matrix. Okay, so what that means is the evolution of your quantum work is completely determined by the spectrum of the normalized adjacency matrix, which is something we can manage right now. Okay, now what if we have another coin? Let's say I weight the global coin slightly differently. So for simplicity, I want to change the weight for one arc, which is the arc point from 1 to 0. So now the matrix well, the arc tail incidence matrix records that change in this row. Okay, and this change is further reflected in the two entries corresponding to vertex 0 and 1. Let me add. This is 0, this is vertex 1, this is 0, this is vertex 1. Okay, so a change in the Grover coin gives you a change in the Hermitian adjacency matrix of the graph. Okay. Now, finally, what if we take a negative Grover coin? Now, this situation is a bit different because instead of projecting onto a one-dimensional subspace, we are projecting onto the orthogonal complement of the O1 vector. So this guy has dimension k-1. Okay, and correspondingly, the matrix that records this information will be large to match that dimension. And on the graph, this looks like we are duplicating the marked vertex k-1 times. And then we put the standard basis vectors, sorry, the basis for the orthogonal complement in the rows for those duplicates. So in this example, k is equal to 3, and then that orthogonal complement is spanned by these vectors that you can take from the Fourier matrix. And so these are just third roots of unity ordered in different ways. And now R star Rn is again a Hermitian adjacency matrix, but it's the matrix of the augmented graph you obtain from X. And you also have to assign this weights correspondingly to those new arcs as well as these old arcs. Okay. So now I'm going to talk about state transfer from one vertex to another, and then I will say what happens if you want to go from all vertices to one vertex. So this part is drawing work Ada Zhan, and you can find a preprint on arXiv. Okay, so if we want to go from one vertex to another, as we mentioned before, this means we want to move from outgoing arcs of A to outgoing arcs of B, in some linear combination. And most naturally, you want the linear combination to respect the arc tail incidence matrix. So, so both initial and final states will lie in the column space of this guy, which gives you the coin. Okay, and under that assumption, turns out that the states are strongly cospectral with respect to U if and only if the vertices are strongly cospectral with respect to the Hermitian matrix. So this is a very nice reduction. You can forget about the transition matrix, the product of two matrices. All you need to worry about is whether A and B, they are strongly cospectral with respect to that. Okay, so let me show you some example. Again, the diamond graph, the Hermitian matrix we saw before is the normalized adjacency matrix. And you can see that actually there are two pairs of strongly cospectral vertices, 0 and 3, and 1 and 2. Okay, and these are the eigen projections of H. So the eigenvalues, not all the eigenvalues lie in the eigenvalue support. Actually, only 1/10, 1/2, and 1. Oh, sorry. 1, 0, and -2/3 lie in the eigenvalue support. And then you can see that this column is equal to the first column. Here, the column is negative for the first column. And finally, this column is positive column. So we are back in our usual sense of strongly cospectral. That is, you have a plus set and minus set. And what if you have a Hermitian adjacency matrix? Suppose your graph is oriented, then you can assign I in one direction, and negative I in the other direction. Then for this graph, you also see strong cospectrality between all the vertices, but now your eigenvalue support is partitioned into 4 groups, because in the first eigenvalue, you see column 4 is omega cube of column 1. And this is omega of the first column, and here you have omega fifth, and here you have omega sevens. So we no longer have this plus and minus set. Instead, we have this 1 set, 3 set, 5 set, and 7 set. And this idea generalized to larger Hermitian matrices as well. Okay, so so following the convention in continuous works, we say two vertices are M strongly cospectral if when you write one projection as a scalar multiple of the other projection, the scalar here is mth roots of unity for some integer m, and we will assume m is minimum. So at least one of these m alpha lambdas will be a primitive mth roots of unity. And similarly, we can partition the eigenvalue support according to the powers of that mth roots of unity that appear as a scalar. Okay, so in the worst case, you will just have m disjoint sets. And here's a characterization for PGST. Assuming your vertices are M strongly cospectral, then this can only happen if M is even. And moreover, in the partition, you only have 2 classes instead of M classes. And you can see this is related to the classical case, because when M is equal to 2, this is the plus set, and this is the minus set. Okay, so we are not too far from the usual case. And finally, by Cronex's theorem, we want the arc cosine of the lambdas to be somewhat linearly independent over the rationals. And the reason is because each lambda gives you the eigenvalue of u in this way. So e to the plus minus I theta is an eigenvalue of u, and you can write it as lambda plus I root 1 minus lambda squared. Okay, so you want the linear combination of these angles to be somehow linearly, you want something happen to a linear combination of these angles. Okay, so here is sample. On the hypercube of diameter 5, we know that the antipodal vertices are strongly cospectral in the usual sense. And now if we take the normalized adjacency matrix, the eigenvalues just get divided by the valency 5. And you can see that it splits into 2 classes, the +1 and -1. And now for PGST, we want the following implication to hold. So this may look very complicated, but let me explain before I show you why that's true. So recall that for each of these eigenvalues, it gives rise to 1 or 2 complex eigenvalues of u, right? And then for PGST, we want that if a linear combination of all these angles hold, then something nice happens to the coefficient that appears in your linear combination. So for example, here, because 1 and -1 give you the real eigenvalue, so they only get 1 coefficient. And all the other eigenvalues of the graph give you a pair of conjugate eigenvalues. So you will see positive theta attached to this coefficient and negative theta attached to another coefficient. And now by Cronex's theorem, if PGST happens, then we must have this whenever Li's satisfy this congruent relation modulo 2 pi, then the same Li's must also satisfy this relation. So on the right-hand side, you're throwing all the coefficient in your linear combination and together with the class they belong to. So these L's, they corresponds to the 0 set, so you will do 0 times those. And this corresponds to the 1 set, so you're throwing 1 times all those coefficients. Okay, and we want this to happen. So now, this is a bit complicated to see because in the continuous case, usually the angles here will be, I guess, square roots or at least some radical numbers. So we have some tools from number theory to determine how linearly independent they are. However, in the discrete case, you see these are not so nice. They are almost surely not going to be a rational multiple of pi. So what can we say about the coefficients when that congruence happens? So it turns out there's a really nice result about geodetic angles due to a convex readiness setup. So a number is called a purely geodetic angle if all of its, well, the square of all of its trigonometric functions is either rational or infinite. Equivalently, you only need to look at one of these six numbers. For example, I want the tangent square to be rational or infinite. Okay, and then Conway and the others studied rational linear combinations of geodetic angles, and this is one of the results stated in the original way. So what they mean is, suppose you have a linear combination of angles. Let's call them A1 theta 1 and M theta N is a rational multiple of pi. Okay, then you can group the left-hand side according to the tangents of the angles. So in each group, the tangent of these angles have the same square-free part, and they differ by a scalar multiple. So let's say all of these guys get some multiple of square root 2, and all of these thetas here get multiples of square root 3, and so on. Then this sum being the rational multiple of pi implies that each individual group is a rational multiple of pi. So then we get many rational conditions for free from this one single equation. And that's very helpful because if you look at the previous example, essentially we only have 3 angles in that congruence. This guy is equal to 0, so it doesn't really matter. This guy is equal to pi, okay? And those two are complementary angles of each other. So I can group them as 4 integers times r cosine 1/5 plus some multiple of pi. Okay, and similarly, these two contributes to another angle. So by the previous theorem, we see that because they sum to a rational multiple of pi, so each of them individually must also be a rational multiple of pi. Now, there's a real-known result that says that if the tangent of the rational multiple of pi is a rational number, then the tangent must be either 0 or plus minus 1 or plus minus half. And apparently this is not among those values. So for this guy to be a rational multiple of pi, we must have a 0 coefficient. Similarly for the second expression. And that now forces the last one to be an even multiple of pi, which means this guy has to be congruent to 0 modulo 4. And that's how we show that the Kronecker condition is satisfied. And so PGST happens on the hypercube. Okay, a few more examples. Actually, for every prime with respect to the adjacency matrix, the hypercube always has PGST between the antipode vertices. Okay, and then you can also consider a side adjacency matrix of graphs, which corresponds to double covers. And an infinite example is given by, oh, I forgot about it. It should be a cocktail party graph. They complement. Okay, otherwise it's trivial. And you can also look at a skew adjacency matrix or a Hermitian adjacency matrix where the entries are plus minus I. And here, an example is taken from a line graph of the hypercube. And you take some nice orientation and do the oriented version of the Cohen-T's cover. And they will give you an infinite family of PGST as well. And finally, for the same graph, you may admit PGST with respect to infinite many coins. And the small example I find is on K4, and you have many choices in the Hermitian adjacency matrix. Of course, they will no longer look nice, not roots of unity. Now, you can also study perfect state transfer, which says the vertices are strongly cospectral, and the arc cosine of lambdas satisfies some ratio, ratio condition. And now there are much fewer examples. for the recency matrix, the only one that I know of is the 4 regular circular graphs. And you can also tune the weights so that this happens on the complete bipartite graphs. Now, some open problems in this part. First, we haven't found any characterization of a family of graphs that admit PGST. So I guess the most immediate task is to determine which hypercubes have PGST with respect to the recency matrix, and how about the Johnson graphs. Okay, and for weighted global coins, I guess a natural place to look at PGST is orientations of Cayley graphs, because here we have some tools from group theory. And we also like to characterize M strongly cospectral vertices and see if it has some analogous result to the 2 strongly cospectral vertices. For example, is there any sort of a symmetry matrix that sends one vertex to another? And finally, there are strongly cospectral vertices that are not M strongly cospectral. And can we determine whether PGST occurs or not? So here's an example I stole from Crystal's thesis. And you have a mixed graph here. So some edges are oriented, some are not. So for the oriented edges, you assign I and minus I. And the edge that has both directions, you just keep the 1 there. And then you can see that 2 and 3 are still strongly cospectral here. They differ by the rules of unity. So I guess it's minus I. Wait, no, I. Okay. And this is minus I. However, if you look at the last 2 eigenprojections, the scalar is no longer a root of unity. So how do we determine whether PGST occurs between these 2 vertices? Kronecker theorem may not help in this case, so we'll need more tools. Okay, so that's about transferring states from one vertex to another. Now I want to talk about how you can transfer from all vertices to one vertex. And this is a very recent work. You can find it on arXiv as well. Okay, so this morning, Hajime talked about quantum walk search with respect to a continuous time quantum walks. So I'm gonna offer you the discrete version. Here what happens is you have a special vertex called the marked vertex, and then you assign the negative global coin to that vertex and the usual global coin to all the other vertices. Now the question is, if I start with all 1 vector, meaning that I don't know any information about the vertex, then how close is my state to a state that concentrates on the marked vertex? And this is the fundamental idea of quantum walk search, and it has been studied for many graphs, including complete graphs, distance regular graphs, and strongly regular graphs. Yeah, I guess I'll just skip because I only have 4 more minutes. Right. So in this talk, I'm gonna view that problem from a slightly different perspective. So instead of looking at the instantaneous probability that you find the marked vertex, I'm going to look at the average over a time period. Now, this average converges to a limit as t goes to infinity. So if 1, the limit is large enough, and 2, this sequence converges to the limit fast, then that offers another way to see why quantum walk search is fast on some graphs. So what is this average probability? Well, as before, everything can be written in terms of the spectral decomposition of U. In particular, if Fr is the eigenprojection and X is your initial state, which is all 1s up to a scalar, then this is the limit as the capital T goes to infinity. So for example, for K4, you can compute that very easily, and you see that well, the probability concentrates on some vertices. Well, it's larger. I shouldn't say concentrate, but it's larger on some arcs than the others. Okay. Now for us, we are only interested in the probability that you reach the marked vertex. So we will only care about these 3 entries and take the sum, which is around 0.3. Okay. And we are going to call this the average search probability. That is, on average, how likely are going to find that vertex. Okay, for K4, this probability is not quite impressive, but if you compute that probability for larger complete graphs, then you may be surprised because as n increases, instead of vanishing, this probability gets closer and closer to an asymptote, which is 1/4. So no matter how large your graph is, on average, you always have about a 1/4 success probability of finding a vertex. And more interestingly, this number is also achieved on other distance regular graphs. For example, the Paley graph is the RG of diameter 2, and you see it converges to this line. And for Johnson graph of diameter 3, you also see that, well, at first it decreases, but then it bounces back and gets closer and closer to 1/4. So why does this happen? In our previous discussion, we have seen that the spectrum of U is determined by the spectrum of an augmented graph, where you add the vertex to match the dimension of the coin. So this is the matrix that pretty much determines the evolution of your quantum work. And moreover, if your graph has an equitable partition with respect to A, that means A itself is a singleton in your partition, and the neighbors of A is another class in your partition, then the eigenspaces of A tilde is further related to the eigenspace of the adjacency matrix of X drop A, the vertex deleted subgraph. And of course, I should be more rigorous because lambda is not always an eigenvalue of X drop A. So here, E lambda means the projection onto this kernel space. So when this is equal to 0, lambda is not an eigenvalue. Okay, now using this result, we can show that, well, if you have distance regular graph, then the eigenvalues that do contribute to quantum work search are either -1 or the conjugate pairs that are contributed from the eigenvalues of your vertex deleted subgraph. And moreover, you can express everything in terms of these eigenprojections. So here V is any neighbor of A. It doesn't really matter because the quantum work evolve identically on the neighbors. And the lambda is an eigenvalue of X drop A. Actually, you only care about main eigenvalues because if not, E lambda vanishes here. Okay, and now by interlacing, we know that the eigenvalues of X drop A lies strictly between K minus K and K. Okay, so we have that this lies between 0 and a half. Therefore, the left-hand side is at most 1/4n, which goes to 0 as n goes to infinity. So asymptotically, this first part, which is contributed by -1, doesn't really matter in your limit. Now, for the second part, you can also play the interlacing trick and show that this guy is lower bounded by 1/4 of K over K minus lambda. So the majority part of your average search probability reduces to this expression, which you can think of it as a graph invariant on X drop A. Okay, so what do we know about that expression? Well, we can isolate a copy of the sum of E lambda J E lambda, which is actually the average state in the continuous time quantum work. And the reason why we can do this is because E lambdas are orthogonal to each other and they are idempotent. Now, this is just the spectral decomposition of Ki minus the adjacency matrix of X drop A, or in other words, the inverse of the submatrix you obtain from the Laplacian matrix by removing the marked vertex. Okay. And then we can return this to the right-hand side. And if we know the smallest entry of this guy, okay, let's say that's equal to alpha, then the right-hand side is at least K times alpha times this number. And indeed, because X is distance regular, you can use the tri-diagonal matrices and intersection arrays to show that the minimum row of this matrix is attained exactly at the V0 where V is a neighbor of A. And that entry is equal to n minus 1 over K. Okay, so we have a lower bound of this, which comes from discrete time quantum work, in terms of something coming from continuous time quantum work. Now, the majority part of your average search probability is 1/4n of this guy, which translates into that. So as n goes to infinity, everything boils down to the limit of this guy. Okay, so here's the question: what exactly is the BB entry of that sum as k goes to infinity? So here I'm gonna use the quotient matrix and actually this is the backward direction. I will explain why this one is more useful than the other. And these AIs, BIs, and CIs, they are intersection numbers of your distance regular graphs. And the tri-diagonal matrix here defines a sequence of orthogonal polynomials PI. Basically, you take the characteristic polynomial of the leading I by I submatrix. And that's a monic polynomial, and these guys interlace with each other. And there are some nice properties about them. In particular, if you normalize this by the C's, okay, then the UIs determine the eigenvectors of your tri-diagonal matrix. So suppose lambda is an eigenvalue, then U0 lambda all the way to UD lambda is the eigenvector for T with eigenvalue lambda. And now you can see why I use the backward recurrence, because the same UIs will also give me the eigenvector for the submatrix here, which is quotient of X drop A. And all you have to do is to replace lambda by an eigenvalue for X drop A. Okay, and that gives us a nice way to link the orthogonal polynomials, sorry, the eigenvalues of the eigenprojections of X drop A and X. Okay, and here's the result. Instead of looking at the sum over all eigenvalues, I will only look at the largest eigenvalue and show this is enough. There's a lower bound for the quantity that we are interested in. And this is determined by the ratio of the same orthogonal polynomials evaluated at the eigenvalue of X drop A and the largest eigenvalue of X. And then intuitively speaking, if lambda is close to k, then this should be close to 1. But so I'm very scared by perturbation theory. So I'm not comfortable expressing this using like analytic or Taylor expansions at those epsilons. But among all the papers I can find, there is a very nice result due to Algebraic, Belkan, and Wang, which gives the perturbation bound that follows directly from Courant, Fisher, Wales, main max theorem. And then it basically says that the largest eigenvalue of lambda is lower bounded by the largest eigenvalue of X minus something. Okay, and this is independent of whether you have an analytic expression or not. So then you can just write PD minus 1 as a Taylor expansion of PD minus K. And then you can show that the tails are actually given by this. So if this ratio goes to 0 as K goes to infinity, if this goes to 0 as K goes to infinity, then all the tails do not matter. And we have shown that this guy converges to 1. So that gives us a characterization of which families of the RGs have a 1/4 success probability on average. So here you want to, of course, fix the diameter. And then suppose all the parameters, including number of vertices, the valencies, and the intersection arrays are all parameterized by something called tau. And of course, suppose K increases in tau, then if this converges to 0 as tau goes to infinity, then in your family of the RGs, the average search probability will approach to 1/4 as the valency goes to infinity. And in practice, we don't need to know the information about these intersection arrays. It will be enough to just assume that the valency raised to d minus 1 over the size of the graph approaches 0. And this is true for many families of graphs, for example, the Hanmeng graph and the Johnson graph. Okay, so here's some open questions about going from all to one vertex. The first one is I have no idea what happens if you have multiple marked vertices, but I suspect the spectrum of U will again reduce to some augmented graph where maybe you have to duplicate more than one vertices. And so knowing the spectrum of this augmented graph will help with determining the average probability. And finally, we only answered one question, which is how big is the average search probability? But the other question is how fast does the sequence of your probability approach that limit? Because if it doesn't go fast, then maybe it doesn't help with quantum walk search. So, so maybe the next direction is to look at the mixing time, which is the smallest time step s, so that for all t greater than s, your sequence is epsilon close to the limit. And there are some upper bound on this in terms of the eigenvalues of u. So that's it. I'll stop there. Sorry for going over time.
Thank you, Harmony. Are there any questions for Harmony? You could unmute yourself or type it into the chat and I will read it for her. Okay, I do have a question, Harmony.
Yes.
So in the cases where you found PSD, have you considered seeing if there's still PSD if you change the Grover coin slightly to a slightly different linear combination of the identity and the all ones matrix? Like how strong is this PSD?
Oh, but so do you still want a reflection or you just want any linear combination of INJ?
Maybe any linear combination of INJ.
Yeah, I guess the purpose, I don't know much if we only have machinery to deal with the case when U is a product of two reflections. But if, I guess if your graph is Cayley, then we can say something. And the eigenvalues of U will.
Which coins of the form linear combination of INJ are orthogonal or unitary? There's not much choice.
Are there not others?
Well, I'd have to sit down and do a little calculation, or you can sit down and do a little calculation.
Tom has pointed me to some papers that think that there are other coins that were possible, of which they have maximized and shown the Grover coin is optimal. But maybe in this setting, you also have a Hermitian matrix to work with. So maybe there are some other.
Well, you could take a matrix, a complex matrix where the diagonal terms all have the same norm and the off-diagonal terms all have the same norm and get things of that form. So certainly there are other matrices you can use.
Mm-hmm.
Okay.
Yeah.
Yeah.
Any other questions for Harmony?
I have a question.
Go ahead, Paul.
Let's see, Harmony. So earlier in your slide, you had a number of formulas showing E lambda V or E.
Sorry, which one?
Let's see. No, back further. Go back further.
Back further. Okay.
It was lower. Okay, right there. So E lowercase EV T. Could you say again what?
Oh,
what is
this. Oh, sorry. Yes, this means the V's entry of that vector. So right, so you can write it as EV transpose E lambda, and then 1 transpose is just J, and then E lambda and VV. So that's the same as looking at the VV entry of this matrix.
So so the lowercase EV, what is the definition of that again?
So this is the transpose of the characteristic factor of the vertex V, and V is a neighbor of A.
So EV has just a single entry one.
Yeah, it's something like this.
Yeah. Yeah. Oh, okay. Got it. Yeah. And the bold one is just the all ones vector, I assume.
The bold one, yeah, this one is all ones vector, and this one is all ones matrix.
Right. Okay. Okay. I understand that. Okay. Thank you. That cleared it up.
Any other questions for Harmony? In that case, let's thank Harmony again, and I have a few announcements after the recording starts. So let's thank Harmony.